This morning, Chanan, Ye, and myself, we're going to introduce you to what we believe is a route to fully ab initio electronic structure theory for correlated materials, namely starting not from DFT, but from GW, and combining it with dynamical mean field theory, or more precisely, an extended version of dynamical mean field theory called EDMFT. So before I get started on the formalism, my lecture will be more about the basic concepts behind screening and about, gradually getting you into GW+EDMFT. But before we get there, I would like to spell out a few motivations, and also I would like to give you some reminders or perhaps introduction to the concept of screening in solids. Okay, so first, motivations. So we've seen in previous lectures that as nice as it is, the combination of electronic structure based on density functional theory and dynamical mean field theory comes with some aspects that you can call engineering, and there is nothing dismissive in these terms. It's absolutely fine, but there are some ad hoc things that we have to do, which are not entirely first principles. And the main two things that I'm alluding to is first, what are the values of the U parameter, or more generally the U matrix, right? We've seen that DMFT, of course, does not provide an answer to that. It's a theory that assumes that the U matrix is given to you. And we have to resort either to exploring the parameter space to see what fits best to experiments, or perhaps get guidance from spectroscopy, which can tell us about some values of U, for example, from the distance between the lower and an upper Hubbard band, things like that. So that's the first problem. And the second problem is the infamous double counting, right? So you remember that when we marry together DFT and DMFT, we are really putting together two theories that come from very different perspectives. You could say they even come from very different planets. Density functional theory is based on a function of the local density, as the name goes. And of course, part of the Coulomb interaction is included. There is a part which is very clearly included, which is just the Hartree term. But there is also part of the Coulomb interaction which is included in the exchange correlation functional and all its different approximations, and which part is included in a specific approximation of the functional, and which part is left out, so which contribution to the exchange correlation energy is left out, is very difficult to, is essentially impossible to understand from a controlled diagrammatic point of view, because DFT is not formulated in terms of Green's function and perturbation theory. It's formulated in terms of a non-perturbative function of the local density. In contrast, DMFT is a theory which is based on the Green's function. We know exactly which diagrams are taken into account in DMFT. There is a certain locality assumption there. And disentangling what's in one theory and in the other is very difficult. There are some attempts to do that. For example, Christian Howley has a nice proposal for so-called exact double counting. But I would say, on general grounds, that this is still a somewhat, it's a prescription that you have to include. Why is this important? Because if we deal, for example, let me just take the example of an oxide. In an oxide, we would typically have some D-like states, okay, which are active near Fermi level, right? And then we would have some other states, say oxygen states, which are below the Fermi level. Of course, when I'm talking about D-like states, they are hybridized DP, and the oxygens also have hybridization with the Ds. And the double counting correction is something which is going to be, in practice, a way to tune the splitting between the P and the D states, right? So you see that there is something intrinsically ad hoc about it. Furthermore, even if we don't talk about the combination of DFT and DMFT, DFT, when approximated by an approximate functional, has its own limitations. You know that the gap of semiconductors does not come out to be right. In the same way here, the distance between these two families of states is not going to be right for a specific approximation of the functional. So we want to overcome these questions. Now, the last point I want to make in terms of motivations is that these two aspects are actually not disconnected. They're actually connected to one another. Why is that? Imagine I decide to apply DFT plus DMFT in sort of a massively downfolded way. I would do that, for example, by constructing Vanier functions, which are going to be quite extended, constructed from a narrow family of states, which are those states here near Fermi level, right? So if I do that, and if this manifold of states here is fairly separated from the rest, I may not have a double counting problem. I'm going to essentially treat a sort of effective model that deals with this isolated manifold. But on the other hand, because I'm focusing on a very downfolded model, I expect the effective interactions U that I have to use to be very, very screened, very different from the typical value of U at the atomic level. By that I mean if you take matrix elements of the Baire-Coulomb interaction in atomic orbitals, very localized orbitals, in a typical oxide, for example, you're going to obtain matrix elements which are on the scale of 20, 25 eV. But obviously, the thing you will have to take into account in this low energy description is way, way smaller than that. It's going to be a few eV, and this is because of screening. Otherwise, all materials would be multi-insulators, right? So that's one option you have, but because of this massive screening, you have to really do a good job at estimating these U's. On the other hand, you may want to construct Vanier functions which are much more localized, much more atomic-like by considering a very large window, in which case you may have a better empirical control on the values of U. We know from various spectroscopies, RIGS, XAS, photoemission, and so on, that, for example, in nickel oxide, the typical U on nickel is screen U, but from a wide window perspective, is going to be something like 8 eV. You can't fiddle too much with this. It's not 4 eV and it's not 20 eV, right? On the other hand, since you've used this localized Vanier function and retained many bands in your description, you will have to face the double counting problem big time. So you see that these two aspects are really untangled, right? And if you want to try to solve one, you'd better solve the other at the same time. And this is the aim of GW+EDMFT and perhaps extension GW+++EDMFT. Okay, so I think this is basically enough for sort of introductions and motivations. And now I want to turn a new page and sort of introduce you to the concept of screening. I'm sure this is actually not an introduction for many of you, because this is kind of a basic knowledge in solid-state physics, but I guess a refresher is always something reasonably useful. Okay, so what is screening about? Well, the concept of screening is something you have all heard about, I guess, which is the following. If we have a charge in the vacuum, right, we all know that it creates a Coulomb potential, right? And that the resulting Coulomb interaction between two isolated charge, V of R, right, is going to be something like, if it's an electron with charge E squared over 4 pi epsilon 0, 1 over R, right? Okay. Now, this is in vacuum. If I am in a material, when you introduce a charge in the system, let's imagine this Gedanken experiment where we introduce a test charge in the system, all the other electrons in the system are going to rearrange. There will be a density perturbation, right? And hence, the actual potential seen by another charge somewhere else is not going to be the bare one. It's going to be affected by this rearrangement of electrons. And that's the phenomenon of screening. And this is a phenomenon which is dependent on distance, because the long distance behavior of the effective screen interaction, which we're going to call always in this lecture W of R, is not necessarily 1 over R. We're going to see that it's not in metals. And furthermore, it's an energy-dependent phenomena, or time-dependent phenomena. It's a retarded phenomenon, because when you introduce a charge at time t, it takes some time for the other charge to rearrange. Physically, you can guess that if I introduce a charge perturbation, which comes with a very, very, very high frequency, the other electrons will not have time to rearrange. And hence, I expect that at very high frequency or very short time scale, there is just no screening. Right? But if I am at low energy and giving time to the electrons to rearrange, there will be screening. So this W of R is really not W of R, but it's a W of R and omega. Right? And it's even a little more complicated. That would be in an electron gas. But in a real solid, it's even a little worse than that, because in a real solid, translation invariance is broken. Only discrete translation invariance is preserved by the crystal lattice. And hence, W of R is really not just a function of distance, but it is a function of both R and R prime and omega. So the screen interaction is the object we're going to have to focus on and try to calculate. Okay, so I'm going to start with very simple description of screening, say in the electron gas, where we have translation invariance, and within a certain simple approximation, which is called the random phase approximation. First, let me set some notations. Of course, pi is equal to E, is equal to 2, is equal to 1. In my notations, no. Just to be a little more serious, I'm going to choose CGS units with a bleeding heart from the European that I am, in which 4 pi epsilon 0 is equal to 1. Okay? And I'm also going to set E to be 1. And because the founding people of electrostatics have decided that the charge of the electron is negative, which is extremely unfortunate, you will have to remember that in these notations, the charge density is the opposite of the density itself. This minus sign is the subject of some headaches, so please keep it in mind. In reality, it's minus E times N over R, but I set E equal 1. Okay, so this is my system of units. Occasionally, I will reintroduce epsilon 0, but usually not. So in this system of units, the Coulomb interaction V of R that I wrote before in vacuum becomes just 1 over R. This is very convenient, right? And its Fourier transform, V of Q, is hence 4 pi over Q square. And one thing which will play a role in the following is the Poisson equation. The Poisson equation relates the electrostatic potential created by the charge density to the charge density itself. And with these conventions, it's given by Laplacian phi. Phi is the electrostatic potential, equal minus 4 pi rho of r. For adepts of the SI units, it would be minus rho of r over epsilon naught, right? And this is plus 4 pi n over. Okay. Good. So now let me do linear response to describe screening, say, in something like the electron gas, otherwise called RPA for reasons that are never so clear to me. But let me do that. Okay, so I'm going to try to describe by linear response the Gedanken experiment, where you introduce a perturbation of the external charge, an external charge density, and see how the system reacts. So if we have an external charge density rho x, maybe I should say delta rho x, but let me just call it rho external, this is going to generate an external potential, which, if I express it by its Fourier component, phi of q, I'm not going to use the different symbols for phi of r and phi of q. I mean, the notation will just be self-evident. This is terrible for mathematicians, but whatever. Phi x of q is going to be v of q, the bare Coulomb potential, time rho x. And why is this? Well, this is because you see the inverse Laplacian, minus 4 pi over Laplacian, is just exactly this 4 pi over q square, which is the Fourier transform of the Coulomb potential. Okay, so this is the external potential due to the test charge, but the system will react by creating an induced charge perturbation in the material, and the induced charge perturbation, charge density perturbation, is a function of q and omega, and it's going to be given by minus, that's because it's the electrostatic charge density is minus the density density perturbation correlation function times the perturbation. So it's going to be given by minus chi naught, which is the famous Linhart function that Hugo introduced in his lectures. Chi naught is the density-density correlator, okay, times the electrostatic potential, but of course, the induced charge density reacts to the total electrostatic potential. So here I should say phi total of q and omega, of q, okay. Q and omega. Okay. So now the only thing I need to do is to actually combine these two things together and write that phi total is, of course, phi external plus the induced charge density, right? And hence, it is equal to phi external minus v of q, chi naught of q and omega, times phi total. And so you see that this equation gives me a self-consistent equation for phi total, which, when I solve it, tells me that the total perturbation of the electrostatic potential is given by the external perturbation that I have introduced, phi external of q and omega, divided by 1 plus v of q, the Fourier transform for pi over q square of the bare interaction, times chi naught of q and omega. If I remember that what I'm really interested in is the effective screen interaction, which I can define as the relation between the total electrostatic potential and the total charge density, so phi total of q and omega. Now I've assumed translation invariance, this is electron gas, equal W, the screen interaction of q and omega, times rho external of Q and omega, right? These two equations immediately lead me to the fact that W of Q and omega is equal to V of Q divided by, sorry, my handwriting is not great, 1 plus V of Q times chi naught of Q and omega. So this formula is called the RPA approximation to screening, or if you want, the mean field approximation to screening. Why is it a mean field approximation? Because I have used the bare density-density correlation function of the system, so it is just at the level of linear response. This is not an exact relation. This is the RPA approximation to screening. So actually, for those of you who like diagrams, you see that I could expand this in powers of V, and this would be something like V minus V chi naught V plus V chi naught V chi naught V minus etc., right? And you immediately recognize, if I denote the effective interaction by, say, a thick line, right, like this, that this is equal to my bare interaction minus, plus this diagram, because you've seen from previous lecture that chi naught is just this bubble, right? And the minus sign comes from the fact that there is a fermionic loop, right? And then the next diagram will be two bubbles, right? And the plus sign comes from the fact that there are two bubbles, and so on, right? So this is the diagrammatic interpretation of RPA, and often it is said that RPA is summing up the bubbles. Something else I want to say is that this formula W equal V over 1 plus V naught chi naught plus V chi naught, sorry. Right? This formula can be cleverly rewritten as V minus V chi naught over 1 plus V chi naught times V, simple algebra, right? And you see that this quantity here, right, is the reducible density-density correlation function. It is the RPA approximation to chi reducible. Reducible because I can disconnect these diagrams by cutting a V line, while chi naught is just the bubble, so it's an irreducible lowest order diagram. Okay. Very good. So this is all formalism. I could also define other quantities. For example, it is often useful to define what is called the dielectric permittivity. The dielectric permittivity simply relates the screen potential W of Q and omega to the bare one by 1 over epsilon longitudinal of Q and omega. And you see that the RPA formula is that epsilon naught over epsilon L. Here I've restored epsilon naught because it makes for a slightly nicer equation, is 1, sorry, is, this thing is clever, it understands mistakes, 1 over 1 plus V chi naught. Okay. By the way, incidentally, please note that this equation is dimensionally correct, which is always a good thing to check when you do a calculation. V has dimension of energy. Chi naught also has dimension of energy. Why is this? Because chi naught is a density-density correlator, right? If I look at the two-time density-density correlation, obviously it's a dimensionless function, because density has no dimension. Well, except 1 over volume, which... and then when I take the Fourier transform, the integral over R takes care of the 1 over the volume. And the Fourier transform over time brings a factor of time, which is 1 over energy, right? So chi naught of Q and omega has the dimension of 1 over energy, and hence this equation is dimensionally correct. Okay, very good. So this is the RPA description of screening, and let me now sort of see what are the physical consequences for that. So the physics now of screening based on the RPA formula. So screening is a spatially and energy or time-dependent phenomena, so I have to discuss which limits I'm taking in this formula. So let me take the limit of static screening, where I send omega to 0 first, and then Q goes to 0. I say this because you may or may not know that, and I don't know if Hugo has described this, but he has? No? Okay. When you compute a two-particle density, a two-particle correlation function in general as a function of Q and omega, the limits Q go to 0 and omega could go to 0 actually don't commute. They correspond to physically different process. And here, if you want to describe the physics of long-distance screening, you first have to take the long time limit, omega goes to 0, and then Q goes to 0. If you do that, and we stay at the level of linear response, chi naught in this limit simply goes to the compressibility of the free electron gas, right? So it goes to kappa naught. That's going to be, now I'm going to have to be a little careful about writing things correctly. So chi naught in this limit would go to kappa 0, which is dn d mu, the compressibility of my free electron gas. Let me put a 0 here, which is a positive number, otherwise the system would be unstable, and proportional to the density of states at the Fermi level, as you can easily see by computing dn d mu in a free electron system. Okay, so what does that mean? Now, if I look at the expression for W, okay, this means that W of Q in this limit, omega goes to 0, okay, is V, which is 4 pi over Q square, over 1 plus V, which is 4 pi over Q square, times kappa naught. And this is 4 pi over Q square plus 4 pi kappa naught. And so you see that now the Fourier transform of the potential is no longer 1 over Q square, but it's 1 over Q square plus a constant term, which is given by the compressibility, which in pedantic term, you could say the photon has acquired a mass. Okay? Because 1 over Q square plus m square is the propagator of a massive boson. Okay? So the screening, the rearrangement of the medium, has generated a mass for the photon. And if you take the Fourier transform of this potential, W of R, always in this limit, omega goes to 0. Okay? This means that it's basically a Yukawa potential. It is something of the form 1 over R times E to the minus Q, sometimes called Thomas Fermi, times R, where Q, Thomas Fermi, you can just read from this expression, is given by Q squared Thomas Fermi equal 4 pi kappa naught. Okay? So we've discovered that screening leads to a Coulomb interaction, which is no longer a Coulomb interaction, but decays exponentially at long distance in the static limit. Now, this is all good as long as kappa naught is finite, right? It's non-zero. But of course, if you are in an insulator, right, the compressibility is going to be 0, because in an insulator, there is a gap. And if there is a gap, it means that N, versus mu has a plateau. I'll try to draw that different color. Has a plateau like that. Hence, d and mu here in the insulator is 0, right? Although, if you want, there is no density of states. Imagine we have just in a simple non-interacting semiconductor, d of epsilon f is 0, hence kappa naught is 0, hence there is no screening, right? There may be a prefactor in front of the 1 over r, so the permittivity is not exactly 1, but it does not decay exponentially at long distance. Okay, so screening is different in a metal and in an insulator, and physically, this is of course because in a metal, there are low energy states that the electrons can take advantage of to rearrange, while in an insulator, they can't because there is a gap, and hence there is no screening at long distance. Okay, very good. So I could go on and elaborate about the consequences of this RPA formula for W of Q and omega at finite Q, finite omega, and so on. I'm going to be a little bit time limited, so I'm not going to really do that. But I just want to mention one important thing, which is the collective mode that exists in such a system, namely the plasma oscillation, right? You probably all know that if you have a system of electrons and some background positive charge, right, and you move this background of electrons, there is a collective oscillation mode, which is called the plasma frequency, which comes with a characteristic frequency omega p square, which is given by n square over m, basically, right? Up to factors of 4 pi and epsilon 0. It's probably 4 pi n square over m in CGS units, or n square over m epsilon 0 in SI units. And this should also show up in my formula. It should show up as a pole in the real part of W of Q. And indeed it does, because if you compute the Linhart function, so I'm going to try to show you a plot. If you compute the Linhart function of an electron gas, and you open a good textbook, you will see that in the omega versus Q plane, right, the Linhart function has the following structure. It has a continuum of it has a continuum region here, which is associated with the particle hole continuum, in which chi naught is going to develop an imaginary part, right? But outside this dashed region, chi naught is purely real, and hence, when you look at 1 plus V of Q chi naught in the denominator, this thing can have a pole. And when you put all this into the RPA formula, what you find is something like this. There is still here a continuum of states, of particle states, but there is now a pole here, right, which starts at Q equals 0 at the plasma frequency. So physically, why is this important? Because what you would expect is that when the frequency is much smaller than the plasma frequency, there is a lot of screening. And when the frequency is much larger than the plasma frequency, then screening is weaker. So this implies that W of omega, right, as a function of omega, you expect to be something like that, right, where there is a low frequency screened value of W and there is a high frequency unscreened value of W. This is roughly happening at omega p, right? And this unscreened value can go at high energy all the way up to the unscreened matrix element of the Baire-Coulomb interaction. So in a typical oxide, I'm not obsessed with oxide, I'm just using this as an example. This could be typically something like 20, 25 eV, while this is going to be a few electron volts, like 3 to 10. And this is all we want to calculate. I mean, this is one of the things we want to calculate. Okay, very good. So let me go back to my other screen. Yes. And let's try to go a little bit beyond RPA. So everything I described up to now is at the RPA level. So let me ask the following question. Can one actually derive an exact relation, no longer approximate at the level of mean field or linear response, between W and chi, the density response function, and of course the bare Coulomb potential. And so the answer to that question is yes. Now let me consider a case in which everything can be a function of R prime, right? And let me redo what I did before, but without assuming just that the density correlation function is the bare one. So what's going to happen? So again, I'm going to impose a small perturbation of the external charge density, delta rho external. This will induce a change in the external. This corresponds to a change in the external electrostatic potential, which is just the bare interaction times delta rho external. If V was not a translation invariance object, this equation should be understood as dr prime V of R and R prime, delta rho external of R prime. Right? So everywhere in the following, when I mean a product, this is really what I mean. The screen interaction, W, of R prime, is going to be defined as the change of the total potential, the external plus the induced one, at site R, when I introduce a perturbation of the external charge density at position R prime. So this is the definition of the screen potential in all its generality. Okay? I'm also going to define the density correlation function, chi of R prime, and in principle T and T prime, but of course, usually we have time translation invariance, so it's going to be a function of T minus T prime. This is what? This is delta n. Again, delta rho is minus delta n for unfortunate reasons. Delta n of R and T divided by delta phi external of R prime and T prime. And from just general correlation function theory, this is the connected correlation function of the density. So this is n of R and T minus n bar time n. These are operators of R prime and T prime minus the average density. Okay, so it's the connected density correlation function of the full system, of the interacting system. Okay. So now you put all these things together exactly as before. You're going to write that delta phi total is equal to delta phi external plus the induced potential, which is minus V delta n. Right? You take into account the fact that delta n is chi times delta phi external. So this is equal to delta phi external minus V chi delta phi external. And since delta phi external is equal to V delta rho external, I can write this as V minus V chi V times delta rho external. And hence, I have derived the following exact equations, that W of R prime, going back to the bare Coulomb interaction, is V of R, delta of R minus R prime, minus V of R chi of R prime times V of R prime. Or if you want in shorthand, W equal V minus V chi V. And of course, I've forgotten to indicate that all this is a function of frequency. Not this guy, but chi of R prime omega is a function of frequency. Okay? So this is, this time, an exact relation, W equal V minus V chi V. And you remember that I rewrote the RPA formula V over 1 plus V chi naught exactly in this form, where chi was taking the form of the RPA formula, right? Chi equal chi naught over 1 plus V chi naught. And so the RPA formula is just saying that chi is chi naught over 1 plus V chi naught. Okay. Good. So this relation, W equal V minus V chi V, is completely general. It applies to a solid. It could apply to an impurity problem, for example, and we're going to use it in the EDMFT construction, so please keep this in mind. Very good. So one last piece of formalism I need to introduce is really just a definition. It's called, what is called the irreducible polarizability. It's a little bit of a big word. Polarizability. And what is the irreducible polarizability? Well, you can view it as playing the same role than what the self-energy does for the Green's function. So when you have a Green's function, interacting Green's function G, we can define a self-energy from G minus 1 equal the bare Green's function minus sigma. This is the Dyson equation, right? Exactly in the same manner, when we have a screen interaction W, I can take its inverse. So the inverse is an inverse in the sense of an inverse of an operator W of R prime in space, right? If it was time translation, if it was a spatially translational invariant, the kernel would just be 1 over W of Q, but in general you have to invert the two position function, and that gives you some sort of Green's function. So W minus 1, I can write that V minus 1, where V is the bare Coulomb potential, minus what plays the role of a self-energy, and this is my irreducible polarizability pi. Okay? And so in terms of this pi, you see that this equation can also be written W equal V over 1 minus pi V, which is something which is often used in the theory of screening. And the yes, well, that's the relation between W and. So these are definitions that you need to keep in mind. Okay, very good. So I think in terms of formalism, this is all about all that I need. And now we can move on and see what we are going to do with all this in the context of embedding methods. Are there questions about any of this, first of all? I think it's very clear. I can take a break to take a bit of tea. Okay. So now, armed with all this, I would like to ask sort of a physics question, which is, what is U in a material or in a solid? So this was the question that was plaguing us with DFT plus DMFT, because nobody really knows what U is. We put a U in the Kanamori Hamiltonian, for example, But conceptually, what really is U and how we should calculate it is not entirely clear, right? So this question receives a unique answer, at least I'm not sure it's unique, but it's a very clear answer in the context of an embedding approach. You remember that at the heart of embedding theories like DMFT is the notion of representability. So imagine some omniscient person gives me the full interacting Green's function g of r prime and omega in the continuum of a given solid, let's say nickel oxide. Right? And you tell me which localized orbitals I'm going to choose to describe my correlated subspace. Let me call them chi-m of R. Right? Then I can do the projection of my full Green's function onto my correlated subspace by doing G M1, M2 of omega equal integral dr dr prime of chi M1 star of R, G of R prime and omega, chi M2 of R prime. This is what you've seen in the lectures by Olivier Gingras and in the tutorials by Harry, Jenny, and co-workers, where we have projectors, right? For example, in the modest implementation, the projectors are precisely matrix element of the chi-m's with the sign UK. So the projector allows me to project the Green's function of the solid onto my correlated subspace. And the representability context is that I'm going to represent this object, right, by a quantum impurity problem with a suitably chosen dynamical mean field or hybridization function of quantum Weiss field, depending on your choice of terminology, delta of omega, and I should add also a set of level position or a matrix of level positions, right, which define my quantum impurity problem. But you see that when I do that, again, as I emphasized in yesterday's lecture, we have to postulate some mu. And so it's not a full representation of what's going on in the solid. It's a representation modulo the fact that we know the U. But now, let me imagine that the same omniscient person not only gives me G of R prime and omega, but also gives me the full screen interaction in the solid, W of R prime of omega. Then I can do the same job. I can project W of R prime and omega onto my correlated subspace. So Chanan, in his lecture, I'm sure is going to explain a bit more how we go from a one-particle set of orbitals to proper representation of two-particle objects. Let me be a bit sloppy about this. From W of R prime of omega, we can construct a tensor W M1, M2, M3, M4 of omega, which is now the projected W onto the correlated subspace, which will be some matrix element of W R prime and omega using some appropriate basis functions for two-particle objects in the correlated subspace. If I was very sloppy, I would write here something like chi star M1, chi star M2, chi, perhaps chi M2, chi star M3, chi M4, and take the integrals, right? But this is not exactly right because this thing is very overcomplete, so you would have to define a more proper basis set, but morally it is something like this, right? It is projecting W onto the correlated subspace. So now I have two objects, GM1, M2 of omega, and this tensor W of omega projected onto the correlated subspace. And I can ask, can I represent these two objects simultaneously by a quantum impurity problem? So now, of course, since I have two objects, I need two Weiss fields, if you want. One is the usual delta conjugate to G, plus the level position. But the other one is going to be the conjugate object to my, so I call this G local. G local is a shorthand for this object, for the projection of G onto the correlated subspace. And W local is similarly a shorthand for the projection of W on the correlated subspace. And similar to delta, there is a quantity which is dual to W at the level of the impurity problem. And this is something that I can legitimately call U of omega. So U of omega is in principle also a four-index tensor, right? Which is such that by solving a quantum impurity model, which is entirely specified by a set of level positions, delta, these are all matrices, okay? And this four-index tensor U of omega, right? By solving this model, I'm going to exactly reproduce G and local and W local. And now you see that this is a unique prescription, this is a precise prescription for defining what we mean by U in a solid. U in a solid, first of all, can only be defined if we promote U to being a frequency-dependent quantity, because screening is a frequency-dependent concept, right? And it is the set of interaction on my localized correlated sub-Hilbert space, such that when I solve these embedded quantum impurity problems, I reproduce the exact G local and the exact W local of the solid. So this is, if you want, the the embedding vision of how to properly define U in a material. And you see that the price we had to pay is two things. First of all, if we really want to implement something like this in practice, we have to solve quantum impurity models which are not only involving a static interaction, but a full retarded interaction, so that leads to algorithmic questions, how to actually do that efficiently. And we have to include this notion of frequency dependence in U of omega. Okay, at this point, again, this is pure representability or representation. This is not a closed set of equations which tells me anything. So how can we do a closed set of equations? Well, one way to do that is extending the concept of DMFT to this notion of having an embedding which deals not only with G, but with G and W. So that has been quoted with a bit of a lack of imagination as extended DMFT, or EDMFT. And this goes back to the mid-90s, a bunch of papers by myself and Anirvan Sen-Gupta, Chimia Aussi, and Chris Lelewin-Smith, and Gabi Kotlia, and so on, in different contexts. But the idea is very simple. Imagine we want to solve some model that has some long-range interaction V of R, right? And Beer-Green's function G naught. Then the EDMFT construction is to say that we're going to map this problem onto a quantum impurity problem which has a U of omega and a delta of omega. And we're going to make the locality assumption that sigma of the whole problem, of the whole lattice, is equal to sigma impurity. And at the same time, we're going to make the same assumption for the self-energy associated with W, which is the irreducible polarizability pi. So we're going to assume that the polarizability pi is pi of the impurity problem. And this will allow me to close the equations. This means that I solved my impurity problem, which is now involving delta of omega and U of omega. I compute the self-energy sigma impurity and the reducible polarization of the impurity problem by impurity. How do I do this? I do this by first computing the density-density correlation of the impurity problem. So I compute chi impurity of omega. So you see that this is much more demanding because I have to compute not only a single particle Green's function, but a two-particle density-density correlator, local. Okay? With chi impurity of omega, I can define a W impurity of omega, which is related to U and chi by the same relation that I derived before, the exact relation, but applied to an impurity problem. So W impurity of omega would be U of omega minus U of omega chi impurity of omega U of omega. U is in the impurity problem, chi impurity I calculate, I get W of impurity of omega, and I define the self-energy pi imp as W minus 1 equal U of omega minus 1 minus pi imp. So by doing all this, I can calculate sigma imp and pi imp. And now I close the equations by using the Dyson equations, right? So I know that G minus 1 of K and omega now for the whole lattice is G naught minus 1 of K and omega minus sigma that I'm going to approximate as sigma imp, right? And similarly, W minus 1 of Q and omega is V of Q minus 1 minus pi that I'm going to approximate as pi imp of omega. And from this, I can recalculate the local quantities by doing sum over K of G naught minus 1 minus sigma imp minus 1. And this should be equal to G local, which I'm going to identify by the representability by 2G imp. And in the same way, sum over Q of VQ minus 1 minus pi imp minus 1 equal W local that I'm going to identify again by the representability assumption to W imp. And these are the two self-consistent closure equations that define EDMFT. Okay, so a few comments on this. First of all, in contrast to the pristine version of dynamical mean field theory for a model, let's say for a Hubbard model, there is no obvious limit in which this theory becomes exact. Dynamical mean field theory is such that if you solve the Hubbard model in the limit of large connectivity on a lattice of large dimensions, you know that DMFT provides the exact solution. There is no such thing with EDMFT. To my knowledge, there is no really model in which you can take the infinite dimensional limit or something like this, for which DMFT would be exact, except with one important exception. If you have random interactions, you can show that if you have random interactions, some quenched disorder on the interactions, like in a spin glass problem, quantum spin glass problem, and Olivier has worked a lot on that, you can show that indeed then extended DMFT-like equations in the spin sector actually solve exactly the model. So apart from this case, in a model without disorder, this is not the case. That's remark one. Remark two is that we cannot apply this directly to a solid. Because in a solid, in a real system, it makes no sense to assume that sigma and pi are momentum independent over all bands and all energy scales. This is crazy, right? So we cannot just be content with EDMFT when we want to do ab initio electronic structure. It may be okay for a single band model with a long-range interaction, maybe a reasonable approximation, perhaps, but it's not going to be okay for a full solid. So we need to do something else. We need to work with a different type of approximation for the bands or for the states that are outside my correlated Hilbert space, for which certainly the momentum dependence of the self-energy and the Q dependence of the polarizability is important, and perhaps do a locality assumption for the correlated Hilbert space. So we need to extend EDMFT, or we need to combine EDMFT with an electronic structure method that can handle the Q and K dependent aspects of screening appropriately for all the bands. And we have such a theory. Such a theory is essentially RPA, a little bit glorified in the sense that it is satisfactory to make RPA self-consistent, which I'm going to explain now, and that's called GW. So the route to follow, to apply these ideas to a solid, is not just to do EDMFT, but to use the GW approach to electronic structure, which is a buzzword for self-consistent RPA, and combine it with EDMFT. And you will see that, at least formally, this approach consistently treats both the question of screening and solves, at least in principle, conceptually, the question of the double counting. Okay, so GW+EDMFT, incidentally, was introduced in its present form in a paper by Ferdi Arya-Setiawan. I'm going to try to get that correctly spelled. Arya-Setiawan. Silke Biermann. Ferdi Arya-Setiawan and myself in the PRL in 2003, so it's not very new. And in also some precursor papers by Kotler and Chitra and Sun and Kotler. Okay, so I have to tell you about GW so that you understand what I'm talking about. And there are two ways to talk about GW. One is the hard way, by introducing functionals of G and W and the Hedin's equation and so on. I doubt I'm going to have time to do that. The other way is to do it in a more pedestrian way, by just arguing about RPA and making RPA self-consistent. So I think this is what I'm going to do. Let's see if at the end of the lecture I have time to say something about functionals and the Hedin equation. Any questions at this point? And since I completely lost track of time because of all this mess with checking out, how much time do I have? What? No, we started at what? 9:05. So I have what? 25 minutes. Okay, great. That's plenty of time. That's going to work. Okay. So let me introduce GW. So we've seen what RPA is about, right? So RPA makes an approximation on the irreducible polarizability. No reason for this should be red. Pi RPA, right, was given by minus the Linhart function chi naught, which in colloquial term is G naught G naught. Again, this expression is a bit of a shorthand. It's a direct product in real space. So it's G naught of R prime T, G naught of R prime R minus T. Or it's a convolution in momentum space and frequency space. You've seen from Hugo's lecture how we calculate these things. So that's the RPA approximation. And similarly, at the same level of, we've seen that in RPA, W, which now I'm going to put a 0 for RPA, okay? W naught was V naught, or V, over 1 plus V chi naught, right? Or V over 1 minus pi RPA or pi naught V. Okay? At the same level of approximation, I can compute the self-energy of the system as the lowest order diagram, which involves my RPA screen interaction W naught and my bare Green's function G naught, and that will give me to sigma RPA equal, again in colloquial term, minus G naught W naught. So this is RPA. Now, I can decide to make these equations fully self-consistent. It's a bit of a jargon. What does that mean? This means that instead of saying that we compute the polarizability with the bare Green's function, we're going to compute the polarizability with the full interacting Green's function. And that's the GW approximation. So this is why I'm saying that GW is nothing else than self-consistent RPA. So in GW, we are going to, let me put this equation now in red. We're going to say that pi at the GW approximation level is not G naught G naught, but is GG. And similarly, sigma at the GW level is not minus G naught W naught, but it is minus GW. But of course, we don't know G and W, right? We only know the Dyson equations, which tell us that G minus 1 is G naught minus 1 minus sigma, and W minus 1 is V minus 1 minus pi. Right? But now, if I replace this by sigma GW, which is written above, and pi GW, which is written above, these four equations are a completely self-consistent set of equations, which are easier to write than to solve. Because you see, there are integral equations, right? What I have to do is start from a guess for G, make this direct product in space, same for G and W, okay? Perhaps I'm going to start from G naught and W naught from RPA, based on, say, Concham DFT calculation. I'm going to calculate G naught and W naught. That will be my first guess. I'm going to do pi naught and sigma naught. Then I'm going to put this into this Dyson equation, invert the whole thing, which usually may require to go to Fourier and frequency space, not necessarily. And then calculate a new pi and sigma, and iterate all this over self-consistency. And in fact, to do that, you need to do it over a massive basis set, including many, many states in your Hilbert space, so many Concham states. and also over all the frequency and momenta. So doing this for a whole solid is a rather formidable enterprise. And in fact, it is only recently that doing fully self-consistent GW on very large energy scales proved to be possible. And the code that has been recently developed by Miguel Morales and Chananier at CCQ, called COKI, is an efficient implementation of this fully self-consistent GW using all sorts of techniques, in particular compression of basis sets, compression of these interaction tensors, and that will be explained in Chanan next lecture. I should really write COKI in green, because the reason this code is called COKI, perhaps Chanan will explain, is due to a little frog from Puerto Rico. So the frog is green. Okay, so this is GW, and in particular, bringing GW to full self-consistent convergence, as I mentioned, is not a simple exercise, but it has one virtue, which is that if you succeed to do that, you have an approach to electronic structure, which is approximate, because we've approximated the polarizability and self-energy by these lowest order diagrams, but which takes into account screening, and which also is independent of the starting point if you do it self-consistently. So you can start from DFT just as a convenience, okay? But once you've iterated to self-consistency, it should be independent of the original starting point, for example, of the original functional you used in your DFT calculation. You may also decide to start not from DFT, but just from Hartree-Fock, or something like this, or Hartree, or whatnot, okay? And you should converge in all the perfect world to the same thing, okay? Now, this is not necessarily perfect. In particular, nothing is telling you that by making this sort of diagrammatic approximation self-consistent, you do a great job or a better job than the bare perturbation theory. So self-consistent perturbation theory comes at your own risk, right? And there are documented examples in which, in fact, making perturbation theory self-consistent in this sense of dressing all the lines of G and W actually makes things worse from a spectroscopic point of view. It can only lower the total energy, because you can show that this can be derived from a functional, so it can only lower the total energy. But from a spectroscopic point of view, it's not entirely clear that this is going to be better. And the reason for this is that, in fact, these equations, which look a little bit ad hoc, can be put onto a much firmer ground using the so-called head-in formalism. So I don't think I will have time to really describe that. The head-in formalism is a seminal paper by Hedin in the 60s, which actually derived a set of exact many-body equations, which for which GW, self-consistent GW, can be seen as a particular approximation. And for the aficionados, let me just quote what the Hedin's equations are. So the Hedin equations are the following. They are actually saying that there is a three-particle vertex. So you were introduced. So what I'm going to say now is kind of a sidebar. If you are not familiar with many-body perturbation theory and diagrams, you don't really need to follow that. I'm going to go back to GW+EDMFT, and I don't need the Hedin equations for that. So just see this as a digression. Okay? But in the Hedin formalism, a key object is the three-particle vertex. The three-particle vertex is something that has two external legs that are electron legs, and an external leg which is the interaction. So it's a triangular object like this. In fact, there is an integral equation which relates the three-particle vertex to the vertex, I'm going to call it lambda, to the vertex, the the two-particle or four-electron line vertex that Hugo introduced in his lecture, which he called gamma. And sort of symbolically, this integral equation for the three-particle vertex is something like this. So that would be gamma, the guy that Hugo introduced. So there is a closed equation that relates gamma and lambda, which is given by this expression. And the head-in formalism is deriving exact expressions for pi and sigma in terms of GW and lambda. It can be shown, that's the head-in equations, that sigma is equal to minus GG lambda, which diagrammatically, GW lambda, which diagrammatically is something like this. You have fermionic line, which is full. You have my interaction W, which is dressed also. And here is my three-particle vertex. Okay? And pi is GG lambda. So it is something like this. So you see that the self-consistent GW approximation amounts to set the vertex to unity in the head-in equations. Okay? So setting a vertex to 1 and deciding that this is how you chop off perturbation theory can be a dangerous thing to do. And in fact, at a certain level, GW+EDMFT tries to repair this for the states for which we believe that vertex corrections are the most important, namely the correlated states. So the states in which there are strong many-body effects. The idea, again, is the idea behind embedding approaches, is that we're going to partition the Hilbert space between all the states of the system and a correlated subspace in which we believe that many-body effects are particularly important, many-body effects that come beyond the GW approximation. So we're going to do the GW approximation of setting lambda to 1 for the states that are far from Fermi level and not so correlated. And we're going to do a non-perturbative treatment, which will include all vertex corrections implicitly, but with a locality approximation for the sub-Hilbert space of correlated states. That's the general idea. Okay, so you can forget this digression about the head-in equations. We've talked about what is U in a solid and the idea of representing the local G and the local W from a quantum impurity problem with retardation. We've talked about the self-consistent GW approximation. Now we're going to put these two things together. And putting these two things together is the GW plus extended DMFT formalism. That I'm going to introduce at least in simple terms right now. So you see that when we do that, in contrast to DFT plus DMFT, we have married together two theories that really come from the same universe. They are both formulated in terms of many-body theory based on Green's function. And we know exactly which diagrams, if you are obsessed by diagrams and perturbation theory, which you may not be, but if you are, we know exactly which terms, let's say, are kept in the theory and which terms are neglected in the theory. And especially we know, when we combine the two, which terms to remove from GW that are going to be correctly handled by EDMFT. And that's very different from marrying DFT plus DMFT, because again, in DFT, there is no way to really identify which terms, from a Green's function many-body point of view, correspond to a specific approximate DFT function. At least, not that I know of. Okay, so how do we combine DFT plus GW and EDMFT? Well, we're going to stop making the too drastic assumption that sigma is completely momentum independent even in any basis, okay? And we're going to say that to compute sigma, the self-energy of the system, which again is a function of R prime omega, we are going to use the GW approximation for states which are not in the correlated embedded subspace, and use the quantum impurity model for states that are within that correlated subspace. So we are going to write that sigma R prime of omega is equal to minus GW. This G and this W are the full G and the full W of the whole solid. So this is G of R prime omega brought to self-consistency in the whole solid. We're going to add to this quantity the self-energy of the impurity problem, which will be parametrized by a U of omega and a delta of omega, which are matrices, of course, in the correlated orbital subspace. And of course, when we do that, we have double counted some stuff, right? But we know what to remove. What we need to remove are the diagrams or the perturbative contribution that would happen in the impurity problem if we were to treat the impurity problem at the level of a local GW approximation. So we have to remove minus G local, W local. Again, these are colloquial notations for the projection of G on the correlated subspace and the projection of W on the correlated subspace. Right? So this is the GW plus EDMFT vision of double counting. We can call this minus sigma double counting if you want. But now we know exactly what it is. And by the same token, we're going to calculate pi, again a function of R prime omega, as being GG. We're going to add to this guy the pi impurity of my quantum impurity problem. And we're going to remove G local, which is, if you want, minus pi double counting. Again, we know exactly what it is. So this is the GW plus EDMFT ansatz for sigma and pi. So now you see that if we were doing just EDMFT for a model, let's say, we would just say sigma of R prime of omega is sigma impurity. We would not have that term. And it wouldn't have momentum dependence. Now this guy, for all the bands that are far from Fermi level, will bring the important momentum dependence. And we know that GW is not doing a bad job for weakly correlated systems, at least for many of them. It's a reasonable approximation for electronic structure, more costly than DFT, but a good way to do electronic structure. So we are benefiting from both worlds, doing electronic structure in a way that can handle less correlated solids at the GW level, and treating strong correlations from an embedding perspective. Okay, so this is the answer for sigma and pi in GW plus EDMFT. Now I have to write all the chain of, the recursive chain of self-consistent equations. So I walk you through the different steps in doing GW plus EDMFT calculation. So let me do the whole chain of steps so that you have that clear in mind. Or if you want the iteration loop. So first, you have to start from some GW calculation. Eventually, if you have a good code, like Coqui, you will bring the whole thing to self-consistency, so it doesn't perhaps matter very much from where you start. You may want to start from G0, W0, but you have to start somewhere. So let's say you start from some GW calculation. Whether the starting point is fully self-consistent or not, it may not be totally important. And you're going to compute pi as a first step in the GW approximation. So pi GW is G, and sigma GW, as we've shown, is minus GW. Okay. Now, we're going to project these guys onto my local embedded Hilbert space. So G I can project into a G local, and W I can project into a W local with a certain choice of local orbitals. And now what we have to do is we have to solve a quantum impurity model, which is parameterized by delta of omega and u of omega, right? Such that these things are reproduced. Then we're going to use our approximation for sigma that I wrote previously, and that implies upfolding. So when I solve the quantum impurity problem, I can obtain sigma impurity and pi impurity. I explained before how to obtain pi impurity. I have to go through this route of computing chi impurity, putting it into W impurity equal U minus U chi U, and then defining pi impurity as W minus 1 equal U minus 1 minus pi. So you have to do all this stuff, right? This will lead you to sigma impurity and pi impurity. Then what you do is you construct, you upfold sigma impurity and pi impurity to the whole solid, and you do sigma equal sigma GW minus the double counting term, which I'm not going to write again, but was minus G local W local plus sigma impurity, pi equal pi GW minus pi double counting plus pi impurity. Right? We're going to now plug this into the Dyson equation and project back. So we're going to compute G local exactly like in DMFT as some projector G0 minus 1 minus sigma, this sigma, okay? Some projector minus 1, and W local as being some projector tilde, which is appropriate for the two particle sector times W minus 1, V minus 1 minus pi minus 1 P tilde. Okay, so this defines G local and W local. And then we're going to iterate the whole thing by redefining new parameters of the impurity problem as U minus 1, again these are all matrices, of omega, equal W local minus 1 plus pi impurity of the previous step. And in the same way, delta of omega, okay, equal something like omega minus the matrix of the levels minus sigma impurity minus G local minus 1. You see this is the G naught minus 1 of the impurity problem. I put this back into the impurity problem. I iterate, right? And what you should do is also iterate over the big loop of the self-consistent GW. So as usual, like in DFT plus DMFT, there are two loops. There is an internal EDMFT loop, which is getting U of omega and delta omega to convergence. But in DFT plus DMFT, there will be an outer loop that I guess Olivier has described, which is the outer charge self-consistent loop over the local charge density. Here is the same story. There is an outer loop over G and W, the full G and W. So this is frankly easier to write on a sheet of paper than to actually implement in practice. And this is why there's been like 20 years between the first papers that proposed this approach about 20 years ago and implementations that were developed over the course of these 20 years with various degrees of approximations. So the number of efforts in the world that has implemented GW+EDMFT is not that large. Just to quote a few of them, there's been a nice effort by Silke Biermann and co-workers in Paris and Palaiseau. There's been also a whole enterprise by Philippe Werner and his collaborators in Fribourg in Switzerland. And there's been also a strong development at Rutgers and Brookhaven National Lab by Gabi Kotlia and Sang-Kuk Choi and their team. Sang-Kuk is now in Korea. And there is now a strong effort at CCQ in the framework of the Coqui code and tricks to implement fully self-consistent GW+EDMFT. There are a couple of other enterprises like this, but it's relatively limited because the whole formalism is pretty, demands a lot of algorithmic and computational developments. However, if you can make this efficient, we believe this is a very nice route to having a fully ab initio electronic structure method for strongly correlated materials. And Chanan will actually show how this is implemented and also, I guess, some examples. So I have borrowed a little slide from Chanan, which, if I can find it here, which sort of illustrates that self-consistent loop. This is just putting in a graph what I described before. So these are the here you have the Dyson equations, the projection procedure, the internal loop, the internal EDMFT self-consistency loop, which is in blue here. Okay, this is all. This can all be done in tricks. While all the things that are in yellow here are currently implemented in the Coqui code, and these two codes talk to one another. Chanan will describe this in more detail, I think, in his lecture. Okay, very good. So I think I'm more or less, my type is more or less up. There are two things that I would like to mention in closing. One is just to mention that this whole formalism can be grounded into a total energy functional. So this is very reassuring. Because we all like to be able to compute total energies from functionals, right? So in previous lectures of this school, you have been exposed to what is called the Baim-Kadanoff function. I'm not going to derive everything, I'm just going to give you a few hints for further reading. The Baim-Kadanoff function was a function of G, the Green's function, which was given by trace log G. So this trace is over everything, space and frequency, minus trace of G naught minus 1 minus G minus 1 times G, plus something called the Luttinger word function that contains all the exchange correlation processes. And this function is stationary with respect to G, which implies that, which basically yields the self-energy as delta phi delta G. I guess this was introduced, no? Okay. So exactly in the same manner, it is possible to construct a function of both G and W. This follows the same conceptual route than this. To construct the Baim-Kadanoff function, you can view it as a Legendre transformation on the total free energy in which you constrain the Green's function to take a certain value G. So you construct a constrained free energy, and in this framework, sigma can be seen as a Lagrange multiplier conjugate to G. In the same way, we can do the same double Legendre transform construction in which we constrain both G and W. And this is something that was done by Almblad and co-workers. I don't exactly remember the dates, but you see there was a lot of high-level many-body theory done in Sweden in those days. So Almblad et al. So again, I'm going to try to spell this correctly. I think that's the correct spelling. And what these people did is that they constructed a function of omega and G and W. And this function has the following form. It's, again, trace log G minus trace of G naught minus 1 minus G minus 1 G. So this starts exactly as the Baim-Kadanoff, because this is the Legendre transform with respect to G. But then it involves minus 1/2 trace log W, very analogous, plus 1/2 trace of V minus 1 minus W minus 1, which really is the polarizability, times W, plus something that generalizes the Luttinger functional to an exchange correlation functional of G and W. And you can formulate GW plus EDMFT as a truncation of that psi functional, which is the following: psi of G and W in GW plus EDMFT is postulated to be minus 1/2 of trace of GWG. If you just stop there, that would be the GW approximation. If you use that functional, which is just the lowest order fully dressed diagram, and you take stationarity, you will derive the GW equations. So psi GW plus DMFT is doing this, removing the local contribution. So we remove minus 1/2 trace of G local, W local, G local. And we add with a minus sign, so, sorry, we add minus 1/2, not minus 1/2, sorry, we add plus psi of the quantum impurity problem, which is a functional of G local and W local. And in this way of seeing things, the quantum impurity problem is just a way, is a machine to generate the non-perturbative exchange correlation functional of G local and W local. So this is the psi-functional for the GW+EDMFT approximation. In this expression, at stationarity, gives you a concrete formula for the total energy of the system. Okay, so that's the first remark I wanted to do. The second remark I wanted to do is that, there is something I didn't talk about, which is called constrained RPA. And constrained RPA is kind of a poor person approach to estimating U and even U of omega in a solid without doing all this machinery of GW+EDMFT, which is more expensive. I have to stop, right? I think. I'm done. It's okay? I'll take 3 minutes, okay, to describe constrained RPA. So what is constrained RPA? Okay? Constrained RPA is a way to estimate. I say estimate because I don't believe that constrained RPA, despite being one of the co-authors of the original paper, I don't believe that constrained RPA is the ultimate answer to what U of omega is in a solid. I think GW+EDMFT with this concept of an embedded U of omega that represents W of omega, if you do a good job solving the quantum impurity problem non-perturbatively, is much more reliable. But it's a cheap way to have at least an estimate. So what is the idea behind that? Well, the idea behind constrained RPA is that we're going to imagine that the only thing we know how to do is RPA. And so in RPA, the polarizability of the system, as we've seen, is given by G0, G0. G0 would be, in the ab initio context, say, the Kohn-Green's function, starting from a DFT calculation. Now, obviously, if I'm going to apply, say, static DMFT, okay, not EDMFT and all that stuff, but just the usual DMFT, if I apply DMFT by selecting a subset of bands, I should not include in my definition of U the screening processes that involve particle Hall transition within the correlated subspace. So imagine I have divided my bands, roughly speaking, into a set of correlated bands that I'm going to draw in red, right? And a set of other ones, which may overlap, but which is going to be something like this. This, roughly speaking, defines my target space for embedding, right? Pi equal G0, G0, if you use spectral representation of G0, means particle Hall transition between empty and occupied bands. And obviously, the particle Hall transitions that would correspond to internal screening processes within the target subspace should not be included in the definition of U for that same target set of states, because this is going to be taken care of by the non-perturbative solution of the impurity problem. Right? So this leads to the idea of partitioning pi into a component which is pi corresponding to those kind of transition, let me call it pi correlated, plus pi, maybe I should put a 0 here, pi naught of the rest of the system. And if I write the RPA equations, it tells me that W minus 1 at the RPA level is V minus 1 minus this pi, okay, which is now pi rest minus pi correlated. And you see that it is very natural to say that this is the screen interaction W rest minus 1 due to all the particle Hall transitions that involve an initial and a final state that are not both in the correlated subspace. So for example, transition like this one or that big one here or this one are all included in pi rest, but not the one the green one that are internal to my target subspace. If I was solving the impurity problem at the RPA level itself, which is usually not such a great thing to do, then that formula would be precisely what I would do. I've just done it in 2 steps. The first step is to do RPA for the rest of the system, and then solve the impurity problem again at the RPA level, which may not be great if these are strongly correlated states. And so in this framework, a first guess for omega is just given by the matrix element of W rest. So if I take now matrix elements of W rest of omega between my correlated state, my correlated wave function, this will give me a first guess for U of omega, which may be reasonable. In fact, empirically, we know that often this gives reasonable trends, but it also overestimates screening somewhat as compared to what we have to put in as a static U in a standard DFT plus DMFT calculation. So I view CRPA as a sort of first guiding principle. The nice thing about CRPA is that it allows you to discuss, for example, how screening depends on the choice of your correlated orbital, so of the width of this window. And I will just show you a plot and then I'll stop. Taken from one of the, it's not the paper I want to show. Oh no, it is. Taken from a paper by Ferdi Aryasetiawan and collaborators, in which the CRPA interactions were U of omega, estimate for U of omega, were calculated for strontium VO3, your favorite material. And it illustrates what I was saying before, namely that you see that this is the real part of U of omega, calculated from CRPA approximation. And it illustrates what I was saying before, that obviously this function is something, look at the real part, this function is something like some value here, roughly speaking, a big jump here, and another value here. This is an unscreened value at high frequency, which is of the order of 15 eV, right? Here obviously must be the plasmon frequency. There is not a single plasmon because it's a multiband system, but there is roughly speaking a plasmon which is around 12 eV or something like this. And there is a screen value of U here, which is anywhere around 3 or 4 electron volt, right? So this is nice. This gives you a relatively cheap way of estimating the effect of screening and an initial guess for U, right? Using not the full machinery of GW plus EDMFT, but just a calculation which involves G0, G0, okay, based on a Kohn-Sham value. But you shouldn't really think that your DFT plus DMFT calculation is going to come out absolutely right if you pick for U that value here at 0 frequency. It could be a little overscreened. Okay, so on these good notes, I will stop there, and I'm happy to answer questions.